Hello, this is Philip Pratt from Texas Instruments, and in this presentation we're going to give you an overview of an interoperability of the Microsemi RTG4 FPGA with the Texas Instruments ADC 12DJ3200, which is a new ADC from TI with a high-speed SerDes link known as JESD204B. The key features of our demonstration today are the ADC 12DJ3200, which is this small 10 by 10 millimeter ADC you see on the red PCB, the serial links back to the FPGA over an FMC connector, and the RTG4 FPGA. In order to give context to the demonstration, it's important to understand what is JESD204B. It is a fairly new JEDEC standard, which is a SerDes link used primarily by high-speed ADCs and DACs connected to ASICs and FPGAs. The data is parsed over a specified number of lanes. It uses 8B 10B encoding for synchronization, clock recovery, and DC balance. The standard supports up to 12.5 gigabits per second lane rate. It has provisions to support deterministic latency across the serialized link. The key clocking requirements are the sample clock, which provides a sampling clock and reference for all other system timing, and the sysref. This is source synchronous to the sample clock and provides phase reference for SerDes frame clocks. A brief history of JESD204. In 2006, the spec began as a relatively basic specification up to 3.125 gigabits per second, but did not provide a lot of the added features that a lot of the system requirements really had in place. Then 204A was added in 2008, where additional capabilities became available, such as multiple lane support and lane synchronization. And then in 2011, with the ratification of 204B, the lane rates went up, and we added all the important specifications, including deterministic latency, which was key to the wide adoption of this specification. The key parameters in JESD204B are often referred to as the LMFS. Here L stands for the number of lanes per converter device, M is the number of converters per device, F is the number of octets per frame, and S is the number of samples per converter per frame clock cycle. The SerDes speeds may vary for each of the LMFS modes. You can have fewer lanes, which increase the lane rate, or you may have more decimation, which decreases the lane rates. Data converter datasheets provide the lane mapping for desired modes and lanes on a per-device basis. You can learn more about the JESD204B spec at Texas Instruments website under a training.ti.com portal known as the High Speed Signal Chain University, with the link provided on the right in this presentation. Here's a block diagram of the demonstration we have today. You see on the right the ADC12DJ3200 evaluation board, which is a two-channel ADC with two analog inputs A and B. The clocking is provided by the devices called the LMX2582 and LMK04828, both clocking chips from Texas Instruments. There's an FMC connector, and we're using 4 lanes in total of SerDes over the FMC connector back to the RTG4 development kit. Here inside the RTG4 FPGA, we have the SerDes interface, the IP controlling the SerDes, and the control logic. And then we pass this data on to the Identify Pro GUI in order to analyze the results. You can see we pass the sync signals and the sysref signals and the reference clocks through the FMC connectors. As mentioned earlier, every ADC and DAC has a specified way of using the JESD204B. In this case, we have different modes from JMode 0 to JMode 18. For the demonstration, we've set the ADC 12DJ3200 into JMode 11. This happens to be a decimate by 4 mode with up to 8 lanes to serve both data converters, and then we have the LMFS set at 4, 2, 2, and 2 as specified in this table. Typically in an ADC or DAC datasheet, you will find a table such as this to identify how that particular device uses the 204B spec. The ADC we have in this demonstration today is a new Texas Instruments ADC12DJ3200. This device has 12 bits of resolution and can run as a dual channel at 3.2 gigasamples per second or a single channel at 6.4 gigasamples per second. It has 3.5 watts of total power consumption, has a 3 dB input bandwidth of over 7 gigahertz, an RF-friendly front end at 800 millivolt peak-to-peak 100 ohm differential load, very good noise floor of 152 dBFS per hertz, very good IMD3 of 65 dBc at an FN of 2.6 gigahertz. And as noted here, it has an optional decimation feature of 2x real or 4/8 or 16x complex, and supports either 8 lanes up to 12.8 gigabits per second or 16 lanes up to 6.4 gigabits per second if you're using all of the data out of the device without the decimation features. This ADC is commonly used in wideband communications, radar, software-defined radio, and oscilloscopes, and is very high performance. The requirements for running the demonstration included the RTG4 development kit, the ADC12 DJ3200 EVM, a function generator to create a sine wave, 5-volt DC power adapter and 12-volt DC power adapter, 2 USB-A to Mini-B cables, and 1 SMA cable. The software requirements are the Microsemi Libero system on a chip software. Here we're using version 11.8, and the ADC12 DJ3200 EVM configuration software, which is the GUI for the eval board. The Microsemi RTG4 development kit includes the RTG4 FPGA, and today we're using primarily the FMC connectors, the 12-volt power supply, the on-off switch, and the USB port. The ADC12 DJ3200 EVM, or evaluation module, contains the Texas Instruments ADC, the Texas Instruments clocking chips, the LMX2582 and LMK04828, the analog inputs, the USB port, the 5-volt power jack, and the FMC connector. The hardware setup for today's demonstration is quite simple. We connect the ADC12 DJ3200 EVM to the RTG4 FPGA development kit over the FMC connector. We have power supplies connected, USB connectors, and now we'll move on to the demonstration. This is the RTG4 interoperability test with the ADC12 DJ3200 EVM. We will start by connecting the 5-volt power supply to the ADC12 DJ3200. Next, we connect the 12-volt power supply to the RTG4. Connect the USB cables to each board. Turn on the RTG4 and you will see status lights illuminated. Next, we will be programming the RTG4 using FlashPro, which is part of the Microsemi Libero software package. Start by creating a new project. Then select Browse, and then the FPGA bitstream file to program the FPGA, then click Program, and wait while the FPGA is programmed. This can take a few moments to complete. You can see the status under Programmer Status. When it is complete, the status will read Run Passed. This means it was successful. Now the RTG4 is programmed with the 204B IP, programmed for the mode we will configure in the ADC. Now we go to the ADC12 DJ3200 GUI. Set the clock to 1000 MHz, select JMode 11, and click Program Clocks and ADC. After it is completed, it should say Hardware Connected on the lower right and Idle on the lower left. The tabs for Control and JEST204B are left to their defaults for now. The NCO configuration tab can be used to program the NCO in order to tune your input frequency to a desired new frequency at the ADC outputs after the on-chip digital down converter, which is turned on in this mode. We go to the LMK04828 tab. This is the TI jitter cleaner and clock distribution chip that is on the ADC 12DJ3200 EVM. We're going to use the extra FMC clocks to provide the FPGA a fabric clock of 125 MHz by selecting divide by 8 from our 1000 MHz master clock. Now we will set up our waveform generator to create a 1 MHz tone that is below the 800 mV peak-to-peak full-scale range of the ADC 12DJ3200. Here we select 600 mV peak-to-peak and make sure this is connected to the ADC input on the ADC 12DJ3200 EVM. Now we go to the RTG4 board and we reset the FPGA. Now to see if the FPGA is capturing the data from the ADC, go to Libero and open the demo project. Go to Identify Pro Debug Tool and select Open Interactively. Click Run to start the sample capture, which establishes a connection to Identify Core. Let this run for a moment, then select Stop to capture current samples. It will ask you if you want to stop and download the current samples. Select Yes. Click to open Waveform Display in the top menu item in order to view the waveform and see all the signals being monitored by Identify Pro. Select all 4 of the SerDes lanes labeled Data Out. Click to Data Format, then change the data format to Analog Interpolated. Click on each data out, insert Analog Height extension to be able to see the waveform better. Then zoom out if needed. In case there were issues with the first test, or to see if the JESD204B link is working without an analog signal applied, open the ADC GUI and go to the 204B tab to turn on the 204B ramp test pattern. Then enable the JESD block. Now we go back to Identify Pro and hit the Start button again. Wait for a moment so the ADC has captured some samples to the FPGA, and then hit Stop to download the captured ramp samples. Open the waveform display. First we see in hex format, so change to Analog Interpolated View to view the test ramp after selecting all 4 data out. If you zoom out again, you should see the successful capture of the ramp pattern. The objective today was the successful connection of a Microsemi RTG4 FPGA development kit with the Texas Instruments ADC12DJ3200 high-speed ADC using the high-speed SerDes link JESD204B. Please contact Microsemi or Texas Instruments for more information about today's demonstration. Thank you for watching.